So thanks everyone. Sorry, I transported places because we can put satellites into orbit, but Qantas can't get places reliably. So I'm talking about a project that we've been going on for a couple years now, and it's a bit different obviously from the Cubesats, but it started off with the Cubesat design that migrated to a high-altitude balloon. And that was essentially to do an ultraviolet survey of a telescope mounted to a high-altitude balloon. And we've had some great progress since this last meeting last year. Last year we were gearing up for our first flight, and we've had it. So this is a nice, because as we've heard people like images from space, this is an image from, it's in Earth's atmosphere, it's not quite space, but it's not the first image from Australia, from Australian satellite, but it is an image of Australia from an Australian balloon, so that's something. But it's good, it's progress, we're flying things. So a bit about background on what we're trying to do is we've partnered with a few groups in the US, and this is really born out of work of the Kepler Space Telescope, which recently left this Earth in the way of, it ran out of fuel last weekend. And so what we're trying to do is to upgrade the capability of some of the science that we wanted to do, but the necessary part of it is to actually go towards the ultraviolet. And it's something that we haven't been able to do effectively in astronomy in space. There's three real quick main drivers here. And one is everyone always likes to hear about Earth-like planets. It's always a bit of a misnomer, right? We say it's Earth-like because it's a planet around a sun-like star that's an Earth-like planet, but we don't know if it's habitable. And that's really the problem, is that it could be habitable, but we don't know if there's an atmosphere. We don't know if it can sustain weather or even water. And so there's a big push with all these exoplanets that are being found now to actually understand them. And this is one of the main drivers, is that by looking in the ultraviolet, you can see what we call the planet transit in the ultraviolet. So we look for the planet to move in front of the star, just as an eclipse. But when the planet passes in front of the star, the color of the transit will change. So depending on the composition of the atmosphere, either red light will scatter away, and therefore the ultraviolet transient will look different than one previously measured in, say, the optical or the red colors, things that are done all the time here on the ground. Or it will look no different, which means that the light just passes through and there is no atmosphere. Or even if there's a variable atmosphere, or things like clouds or water molecules that change, the UV scattering and the UV light will change as a function of time. So the UV ends up being a very powerful tool when compared to other colors of light. And so it gives a very good probe on what are the atmospheres of these planets that are being found. We also want to look for exploding stars. So if you look for the moment a star blows up, let's replay this, what you can see is the brilliant flash of the star actually being ripped apart. And this flash is actually a powerful tool in diagnosing the mass and size of the star, which we in turn can use for measuring how big or energetic that star was, and therefore for measuring things like properties of the universe. But the thing is, this happens in the first few minutes to hours, and it's strongest in the ultraviolet. So you have to be looking for a lot of time over a lot of area in the ultraviolet to see this, and we just really don't have that capability here. And something my student led, Ryan, was that when two black holes merge, so these produce gravitational waves, which were quite famous recently because they're actually being detected now. There's an interesting thing that happens, is that the two black holes, as they cross into each other, you actually get a burst of ultraviolet emission. So that is, if you see in these images, there's a bunch of stars and gas left around the center black hole. As they cross, they actually burst in ultraviolet colors actually before the gravitational wave happens, so before the black holes merge. So in fact, by actually measuring the ultraviolet, you can predict when gravitational wave events are going to happen. And Ryan showed in a paper that came out last year, late last year, is that you can actually detect. So the bottom axis is how many we'll detect per 6 months, or per flight. And you can see in some cases, we can be able to detect 1 to 10 of these mergers, so these bursts of things that will precursor gravitational waves, in just one single 6-month flight that we're planning. Now, most ultraviolet astronomy has done from space because you have to get above the atmosphere. Hubble's the best, but it's also hard to get time on, and it's going to die soon, the next few years. Galax and Swift have been other great missions. Galax is also dead. Swift is about to die. So there's this theme here where the only ultraviolet capabilities are either dead or about to be dead. And this is where balloons become an interesting option, is that the ultraviolet light does make it slightly down to the ground, right? So the ultraviolet light is absorbed with the Earth's ozone, which means that if you can get high enough into the Earth's atmosphere, you can actually see ultraviolet light. And this is essentially where high-altitude balloons come from, and why we started this, is that we can do a CubeSat-like mission, but we can do it from a balloon, and the benefits, again, of a balloon are we can reuse the telescope that we mount on it to keep flying it per balloon. So this is actually data from our first flight in December. So what you have is what the sun looks like in green, and we fit it with what our telescope was doing. And so you see on the far left that we actually detect signal all the way up to below 250 nanometers. So the ozone blocks light on the ground from 320 nanometers. So everything left of 320 on this plot is stuff you cannot see on the ground. So this is all stuff that is new that you can uniquely see on a balloon that we cannot see just from a normal telescope. So this first test was really to show that, yes, this is possible, that we can see ultraviolet signal from one of these high-altitude balloons. And so the next gearing up of our flight is to launch do 2 simultaneous launches. So the ozone changes as a function of season. So in the winter hemisphere, you get a higher density of ozone, so therefore a higher blocking of UV light, but it sinks, so it's a little bit lower in atmosphere. In the summer, that density weakens. You can actually see the hole in the ozone emerge, but it pushes up. So we fly between 25 and 35 kilometers, which is really dependently in this bulk where this ozone is fluctuating up and down. So depending on when in the time of year you fly will depend on what you see. So we're going to do a flight where we fly from both Nevada and Puerto Rico, which span a different range in latitudes, and therefore a range in densities to test exactly what this strength ends up being. So what we have is that, we've had our first flights, our full second flights, where we're going to mount to our full balloons, we're looking at for later on in this year. And what will end up being is we'll be flying for about 6 months at a time. And so each telescope will see 7 square degrees of area. And so over the course of the night, we can get about 2,000 square degrees, which is 220 times bigger, rather, than what the Kepler Space Telescope could see. And we can see all the way down to 250 nanometers, whereas that sweet spot for doing the science that we can do. So we've shown that it's possible, and that we've made good success. So now it's kind of put it together that we can get the full sensitivity and length and time that we need. And then away we go with building a bunch of telescopes and mounting them to balloons. So all in there.
Right. Thank you. So I'm going to collect some questions for you, man. So some questions for the presenter, Elias.
What's the weight of the payload that is issued by the balloon?
What's the weight of the payload?
We're around 10 to 12 kilograms, depending on how big the telescope mirror ends up being.
More questions?
Is this the payload they flew last year?
Is this the payload they flew last year?
So this was the one that we were gearing up to fly last year. Oh, so the one we flew at the end of last year, all told, was actually 2 kilograms. So this was just the structure. So this was to get under the 4 kilogram limit for small ones. The telescope system, all mounted correctly, will be 12 kilograms. Yeah.
Any more questions? Yep. Gavin?
Yeah. Thanks, Brett. What sort of resolution do you need for observing the extrasolar planets, seeing the atmospheres rather in the UV?
Resolution on sky of a few arc seconds, that's actually good enough. So our system design is 4 arc-second resolution.
Okay.
So we're only looking at brighter things, but that's all the stuff that's being found that you can study in detail anyways.
And that will be the last question, unfortunately. Thanks, Brad, for presenting over the remotely. Have a safe flight. Thank you, Brad.